All right, let's go over the review. I'll probably do it in a couple of parts. So let's get started. So first, with everything all together, there's some strategies that you can use going into a problem. You've got these kinds of things happening. We've got normal problems. So that's when they're probably going to give you a mean and a standard deviation and then ask you for a percentage or a data value. Okay, your binomial, that's when they say out of a set number of items. Okay, and we also know that it's, a discrete thing, like it's a pair of shoes, or it's a person, or this many successes, and it's an exact number. Exact number. Okay, remember our idea about independence, the fact that you are one thing does not change the probability of the other, and then disjoint. So disjoint looks like this, two separate circles. If they are joint, then there's overlap, and this is not disjoint. So if two things can happen at the same time, then they are not disjoint. Remember, the other word for that is mutually exclusive, is separate. All right. So now, do you have multiple conditional probabilities? Can we use the Venn diagram or the tree diagram? What do we need to use? Okay. And then a lot of times, if we can just think it through, like it says, when the first success is occurring, then that's probably our geometric. All right. So those are all the kinds of things, types of probability that we have together in this unit. All right. So here we go. In our first page here, we've got several normal model problems. Here we then find the z-score. Make sure you say z equals this to indicate that you have the normal model. And so then when we do that, we want to accumulate the area above 22. So that's from that z-score of 2.08 to 99. And that's how we have 1.88% of lava lizards longer than 22 centimeters. Okay, so here they say what is the length of the lizard, so they want to find x at that 90th percentile. And the 90th percentile is that area below. So we're going to inverse norm 0.90, and that's how we get our amount right there. All right, and so then we have our then we set up our equation with our x minus the mean over standard deviation equaling that z-score, and we then algebraically solve for that x. Okay, so here we have a situation where it's out of the next 8 dives. What is the probability? Exactly 5 of those situations. So that is discrete, and we want exactly 5 successes. So that's binomial, 0.73 for a success, and we wanted 5 of those. So then there were 3 failures. Here is the way that we did that in our calculator with our binomial PDF, because it wanted a particular number of successes. All right, here we have this situation, same idea. However, they want to say that this blue-footed booby does not catch a fish until her third attempt. So that's, not a success, and then a success. So that is a geometric situation. You could just multiply that out in your calculator, or if you wanted the shortcut way, we want 0.73 to occur on the third success right there. So 5.32% chance of her success on the third. All right, so now we have a two-way table of data, and we first are asked for some probabilities. So what is the probability that a student, so this is an overall student out of the 150, specializing in tourism, so 45 out of 150. But here we say if a student lives in Isabella, so that's a given that. So given that the student lives in Isabella, and I like to write this out because then that guides me easily into how I set up my fraction. So out of all the Isabella portion, so all of the Isabella is the 60 there in Isabella, and then the tourism and Isabella is the 18. So that's how we get that. Now, we are then asked, are tourism and living on Isabella independent? So you remember that to check for that independence, we are always setting up that situation where we say, is the probability of A, um, so is the probability of A equal to the probability of A given that B has happened? So, is the fact that B has happened change the probability of A? So, then here in this case, what happened was the first two questions kind of led you to that point. So, if I say overall tourism, right here, that's A, and then tourism given Isabella, that's A given B. Well, look, those two percentages were the same. So I kind of didn't have to like redo this problem. A and B did it. So they are independent because the fact that you're from Isabella does not change the rate at which you go into tourism overall. They are both 30%. All right. Now, here was one where you weren't guided through the steps. You had to come up with them on your own. So, are living on Santa Cruz and specializing in science independent events. Now, you could have done this the other way where you said probability of Santa Cruz, overall, and then the probability of Santa Cruz given science. Okay. But in my mind, we kind of wonder if the fact that you're from Santa Cruz is going to change the rate at which you go into science. Okay, so either one of these is acceptable, but truthfully, I think doing it the way that I had shown it here in red kind of indicates you understand the context of this problem and you know that you are doing, the explanatory variable is probably where you're coming from. So I had to set this up. Overall science was 51 out of 150. Science out of Santa Cruz. So there were 90 Santa Cruz students, and then 26 were science and Santa Cruz. So looky there. So they are not independent of each other because I can see the fact that you're from Santa Cruz made it less likely that you go into science. All right. And then I said this statistics. This for Santa Cruz versus 34% for science. Okay. You have to have, these are the three pieces you must have written for an independence explanation besides showing this part over here. Okay. So there was nothing extra there. All right. Now, there are several different ways you can do this problem. You could just kind of count some separate pieces in the table, but I did it where I did the formula. It said studying science or living in Isabella. So that's one that is on our formula chart. Science or Isabella was the overall science plus the overall Isabella minus the overlap. So that's what I showed here. The 51 of science plus the 60 of Isabella minus the part that got double counted. And so that is how we get that probability. All right. If a student is randomly selected, so see, this is out of all 150 students, what's the probability the student is studying science and lives on Isabella? So that was just that overlap portion of that 25 over 150. All right. Next. So here we then get some other different situations. So let's go on through these. Here we have, so sometimes students get lost on this problem because it says at least one tortoise from the Galapagos Islands. Um, well, this is just saying that the zoo has a Galapagos turtle tortoise. Okay, so it's not saying like we need to do one minus the probability of none. Okay, so this is a good problem to make you think that just because we see at least one, don't just automatically go, ooh, I need to do that special technique. Stop and think and see if it's one of those ones where it's at least one success. Here, the Galapagos turtles are found in the American zoos, and so the probability that they have at least one tortoise is 0.4. All right, so that doesn't mean we want to find at least one of the zoos. All right, we have 75 zoos we are studying. What's the probability that not more than 20? So that's the number of successes that we have out of the 75 is not more than 20. And you know what? I don't know why, but that not more than 20 always messes with my mind. I have to say, okay, not more than 20 means as long as it's not more than 20. So 21, just as long as it's not more than 20. So 20, so 20 and below is okay, not more than 20. Okay, see, it's still messing with me. All right, so I've got less than or equal to 20. And so then we have our 0 success. See, this is a sequence we're going to be accumulating, and it is binomial because it was out of a set number n. Okay? All right, so I have my accumulation, and accumulation does occur from the bottom. So it will occur from 0 up to and including this number right here. So that is up to and including 20 successes. Okay, so that's why I do have that 20 there, because as long as it's not more than 20, so 20 is included. All right. Next, so this is interesting. I did not give you a hint on this one. There are 11 turtles that are numbered 1 to 11. And so that means you're going to randomly select a group of 5 turtles. And we want to know what's the probability of all of them having an odd number. So you kind of had to, step away from just making an assumption that it's out of 11, choose 5 successes or whatever it was. Because what happens is when you pull one of those turtles out, you don't replace it. So here we don't have an independence situation. And actually, that's what question B asked. Why is this not a binomial problem? And it's not, because when we remove a turtle, we keep it out. And that changes the probability of getting an odd turtle on the remaining trials. So, therefore, that independence condition is violated. So, see, we have this situation where we start with 6 odd out of the 11, and then I only have 5 left out of the 10, and 4 left out of the 9. And then I went down 5 turtles that I collected out of those 11. All right. Okay, so here we have Lonesome George, and we've got multiple conditional probabilities, because depending on who Lonesome George chooses to go and mate with, that will affect the rate at which he is successful in having babies, or being having some offspring. So here we go. So we know that 50% of the time he will not mate, but 30% of the time he'll go to Isabella, and 20% of the time Fiona. However, they have different, but conditional upon who he mates with. There's 25% chance of being successful with Isabella, but only a 40% chance of being successful with Fiona. So then the question is this: if Lonesome George has an offspring, so that means he had an offspring somehow. So I think in green here, I boxed in the ways that he can have offspring. So that's the total, the denominator of the ways he can have offspring. What's the probability that it was with Fiona? So the part that will be on top is this Fiona piece. So here's what that looks like. See, what's the probability he mated with Fiona given that there is offspring? So out of all the ways he could have babies, that's the Isabella babies plus the Fiona babies. So that's the total denominator. But then the top part was Fiona. So it's a little over half, a little over 51%, 51.61% chance that if he has offspring, then Fiona is the mother. All right. Here we go. Next. So here we have this situation where when I was reading it, I thought it, and by the way, it's supposed to be, they list farming with their things, not faming, whatever that is. Okay. So there's my typo. So here we have this situation, and it just naturally kind of read to me where we have some overlap, and I felt that I could see it as a Venn diagram. Some of you choose to draw it as a two-way table, and that's fine. I didn't take the time to do both. Now, what I want to mention to you is to be careful, because it didn't just say how many of them do not fish or farm, which there are 48 that do not fish or farm, but that's not the answer. Okay. It says what's the probability that a randomly selected family does not fish or farm. So that means 48 of them do not out of the 120. So that's 40%. And I guarantee you, if this was a multiple choice question, 48 and 40 would both be options, okay, of the numbers. All right, B, same thing. Not how many families, it's not the 34 that are farming, it's the 34 out of the 120, so that's 28.3%. And I guarantee you 34 and 28 would both be options here, okay? All right. Given that the family fishes, so here is out of all the fish ones, the 38 who fish, who are the farming and fishing ones. So that's the 20 over 38. And so that is probability. You probably felt more natural doing that one. All right. Now, here we had some, see, we're told it's approximately normally distributed. So that in itself kind of lent itself to, then I felt, it's normal model stuff that we're going to do then. Make sure you put your items. And this is the key, the top 20%. So being in the top 20% gives me information where I can find the z-score at this location so that the top 20% is above it and the bottom 80% is below it. So that's inverse norm of 0.8. So that's the z-score, okay? And so that was really important. And then you had to come over here and set up your z-score formula. Your 0.8416 equals your x minus your mean over your standard deviation, and then you solve for the x. All right. Now the next one gives us two x values. So then I know I need to get a z-score. See, notice it's z equals this and z equals that. Don't forget, you have to put z equals, or else you won't get credit for demonstrating a normal model. Or you could draw a picture. If you drew this picture here, then that demonstrates the normal model. All right, and so then to get the area between those two locations, I norm CDF to get that cumulative area. So that's about 9.94% of flamingos have that wingspan there between 150 and 160. All right, now this is interesting. See which one would be more unusual. So that is it going to be the one that is 121 or 156? So in order to see which one is more unusual, you need to get the z-scores and compare them. And the one that is farther away from the mean in either direction, see here, this one is negative 2.375, which is farther away than this z-score of positive 2. So that is the one. The flamingo with 121 is more unusual because it is more standard deviations away from the mean. You have to say that when it is asking you to explain, which if it's a free response, it will. All right, now we've got just some pretty straightforward ones here. We had 10 employed women, so that's a set N. So therefore, we have a binomial situation. And so exactly 2 of them have never been married, so 10 choose exactly 2. So that's just setting up that binomial there. At most 2. So that means 0, 1, and 2. So I want from 0 successes plus 1 success plus 2. So you could add together PDF of 0 plus PDF of 1 plus PDF of 2. Or I could just accumulate up to and including 2 successes. All right. Next. Oh, here we go. At least 8. Have been married. Careful, careful, careful. The previous questions have been about that 20% that have not been married. So I then do this problem, and it's fine, but I just think of my success as the proportion who have been married, and that's 0.8. And then I just go from there. So I want at least 8 of these ones that have been married. So I want 8, 9, and 10. So you can add PDF of 8 plus PDF of 9 plus PDF of 10, or 1 minus the accumulation of 7 and below. You want to take off 7 and below. Okay? And so then that's why I have a 7 right here, because that's what I'm taking off. All right. And then number 14. I thought this first one is so tricky. Wow, because it just really kind of makes you have to slow down and stop and think of these problems. Okay. So look at this one. It's about doing an excavation, 5% are this special of pottery that you find, are this special kind, Socorro black on white. Okay. Look at question A. What is the probability that the 5th shard examined is Socorro black and white? So the reason this is tricky is because it doesn't say the 5th shard is the first one that is Socorro black on white. If it had asked that, then you would do 4 of the 0.95s and then the 0.05. But it doesn't say is the first one that is Socorro black and white. It just says, look at that 5th one. What's the probability? That 5th one is Socorro black on white. Well, the idea is they're independent. This is independent from the next choice, and so therefore you just say 5% because it's just asking about that one event. Okay, that's a tricky one. Tricky, tricky, tricky. I can't remember if that one got me the first time. I think it might have when I first did that problem. All right, now we have one where we're defining the first one that you find is on the 10th trial. So then that's 9 failures, and then the 10th is a success. So that's our PDF of putting that 9th one there. Okay, now looky here. More than 3 pot shards have been examined before finding the first Socorro black on white. So that's interesting. So there's actually a couple of ways you can think about this. So more than 3 have to be examined means the first success that occurs is on the 4th trial or afterwards. Okay, so we know that. The first success is the 4th or the 5th or the 6th or all those other things. 100%, all that stuff out there except for this piece that's in front. So there's 2 ways to think about this. Option 1, you can think, okay, in order for the 4th trial to be the first time you have a success, what's that saying? Well, it just says the first 3 are failures. So you could do 0.95 to the 3rd power to get your probability. So we need the first 3 to be a failure, and then whatever happens after that is what they want. Whatever that is. And apparently that's about 16% of stuff. Okay, option 2. Maybe you think the first success is on the 4th trial. So that means that it is not the first success occurring on the 1st or the 2nd or the 3rd one. So it's everything except a success on the 1st or the 2nd or the 3rd. And so this is kind of a longer process, but it's equally valid. And so with your calculator, you can do your 1 minus your geometric CDF, because that puts the success on up to and including the 3rd place. Success in the 1st, success on the 2nd, or success on the third. See, and that comes out to be the same probability. So people's brains think of these differently. I mean, it took me a long time before I could kind of see both of these options interchangeably. So whichever one way you think of it is correct, and that's fine. Okay, next, number 15. Here we have a couple of more ones. We have out of 50 randomly selected people. So we have a set N. That's our binomial situation. So no more than 9. So as long as it's 9 or less, we are good to go. So that's 0 successes up to 9 successes. So that's the pattern I have to show. What's in red is what you have to show. What's in blue is just what you do in the background in your calculator to get that answer easily. All right, and then here we go on this next one. More than 6 means the successes you want are from 7 up to 50. So you can also, let's see, you could have also typed this here as the probability that X is greater than or equal to 7. Okay, so that's interesting. That's another way that you could have written that. Okay, greater than or equal to 7, or say just greater than 6. Okay, those would be the same. So, but when you show, of course, your work, you have to show the sequence of the first one up to the last one that you want. But calculator wise, we're going to do 1 minus the part I do not want, and the part I don't want. Ooh, I have this wrong. Okay, well, let me check that. Here we go. So wait, let's see. I want greater than 6, so I want to take off 6 and below. So I need to have this right here as a 6. So I need to go and fix that in my calculator because this may not be the answer. See how tricky that is? Okay, so it's what do I want to take off? So in fact, I wrote it over here on the side. Take off the bottom 6 successes. So this should be a 6 right here where I had written 7. Okay, so you can go recalculate that, but otherwise that is going to be the probability. And I'll fix that on the answer key I post. All right. What is the expected value? Oh, expected value is the mean. Expected value is the mean. Geometric 1 over p. Binomial n times p. Okay, and those are on your formula chart. Okay, so since we have a set number of n, that's 50, that is our binomial. And then it asks for the standard deviation. So that's a formula also. So you just fill in those formulas. And 16, that's happening because we're asked, we have a binomial, we have 273 campers. All right, so we've got this probability of getting poison ivy. We know it's about 8% usually get the poison ivy in the summer. So we expect over the course of the summer, about 21.84 campers on average are going to get poison ivy with this standard deviation. Now, the next question is important. How many children would it take you to give you statistical evidence that there's a problem going on there and that there's a lot more poison ivy than you have had in the past? So so we need an upper outlier. So if we had the mean plus 2 standard deviations, that's 30.8. So think about this. 30.8 is your outlier fence. So what's unusual? Is 30 unusual? And that answer is no. That's actually inside the outlier fence, so that's not unusual. It has to be 31 or more to be unusual and to say, oh, we need to get professional growth in here or professional help because we have overgrowth of the poison ivy. Okay, has to be 31 plus to be an outlier. All right, I think I'm going to stop this video right here and then I'll do the AP questions, which is the next portion on the second video.